Okay, this lecture is about starting to represent 3D rotations of a single rigid body. And this will be part of a bigger subject of 3D kinematics. The word kinematics means the geometry and calculus of representing and describing movement. Okay, so let's talk about representing the motion of a three-dimensional rigid body. So imagine you had a 3D rigid body like so. And you threw it up in the air. And it's translating, in other words, it's changing position, but also rotating, let's say, okay? It's translating and rotating. So it's changing position and also changing orientation. Translation means change in position. Rotation means change in orientation. Okay, now if you have an object doing that, how do we represent its change in position and change in orientation in 3D? Okay, so let's say this is in 3D. Okay, so how do we do that? At least one way of describing the three-dimensional position and orientation of a rigid body is to first attach a reference frame to it. So you have this rigid body and you attach to it a reference frame. Okay, and then when the object changes position and orientation, I don't know, like so perhaps, then the reference frame would have changed in position and orientation as well. Okay, so when you say reference frame, we mean this is a set of axes. Okay, so this would be a body fixed reference frame. So one way to track the 3D position and orientation of a rigid body is to, one, attach a reference frame to the rigid body, and to track how the reference frame moves. In 3D. Okay, so what do we mean by that? A reference frame as we've sort of drawn here is two things. Is a coordinate system for describing the positions and orientations of one, other objects, well, you don't even have to say other objects, and two, well, reference frames, which are also objects, I suppose. And by reference frame, we mean a reference frame is really equal to an origin plus a set of three axes, because we are in 3D, and usually, but not necessarily, mutually perpendicular. Okay, so for instance, we could have, this could be some kind of a reference frame with origin O and these three axes, EX, EY, EZ. And here we have other reference frames. Here we are saying that we are tracking the motion of this rigid body by essentially tracking this body fixed reference frame. Okay, because it's body fixed, it moves with the body like so. And if you want to track the reference frame, or if you do track the reference frame, you've essentially tracked the motion of the rigid body itself. The rigid body is a weird, complicated looking object, potentially, with some arbitrary shape. So tracking the reference frame, which is just this axis, three axes plus an origin, is a simpler object. And the idea is that tracking the simpler object, the reference frame, allows you to track the more complicated object, the rigid body. Okay, so that is not immediately obvious, perhaps, but that is essentially a theorem that tracking a body fixed reference frame is sufficient to describe the motion of a rigid body that is attached to that reference frame. Okay, so that's a reference frame, an origin and a set of three axes. Okay, now here we've sort of labeled the three axes EX, EY, EZ for XYZ axes, and then the origin O. Very often in dynamics problems, we will have lots of reference frames, perhaps because we'll have lots of rigid bodies and you have reference frames, body fixed reference frames attached to each of those rigid bodies. So we may use the notation something like reference frame 0, so something like this to represent reference frame 0 or something like that, okay? Or something like A would mean reference frame A. Okay, it's convenient to have numbers because maybe we'll have n rigid bodies and maybe we will associate a reference frame with each rigid body. So this might be a reference frame 2, etc. Okay, so that's a notation that we are going to use. Okay, so let's look at, so we might have, for instance, some reference frame like so, EX1, EY1, EZ1, and then the origin itself is also indexed O1. So this would be the origin and axes of some reference frame 1. Okay, now how do we represent the rotations of such a reference frame? Let's say we have this reference frame rotate. How do we represent that? So that's the next topic. Rotations of frames. Okay, so let's first consider simple rotations, and we shall describe what we mean by simple rotations. So let's consider a reference frame uh, 0, so EX 0, EY 0, EZ 0, and we get a new reference frame which has the same z-axis, but then we are rotating this reference frame about the z-axis like so, and you get new x and y axes, which are essentially rotated versions of this x-axis by some angle theta, let's say. Okay, so that's the new x1, and that's the new y-axis, and this is angle theta, and this is angle theta. But the z-axis is exactly the same as before. Okay, it's more convenient to write this in sort of a two-dimensional, describe this in a two-dimensional plane. So if you have EX1 and EY1 like so, where you're looking down on EZ1, so sort of looking down like that, and then we have the origin O. In this case, the origin O is basically O1 equals O2. The origins are coincident, okay? So let's just call the origin O for now. In any case, we have a rotation about the z-axis that rotates the x and y axes like so. Okay, z remains the same, x and y change. Okay, so ez naught equals ez1. This is sorry, this should be ex naught, this should be y naught, and this is ex1, this is ey1. Okay, now what is the relationship between ex1, ey1, and ex naught, ey naught? And that we can determine by just trigonometry, classical sort of high school trigonometry essentially, or vector calculus. Okay, now let us write. So what is mathematical relationship? Axes of reference frame 0 and reference frame 1. Okay. So let's write that down. Let's write it in the following manner. Let's write ex1 equals something times ex naught plus something times ey naught plus something times ez naught. Okay, so what is this going to be? This is the component of vector ex1 along ex naught, and then these are etc. Okay, so what is the component of ex1 along ex naught? It's the projection of ex1 onto ex naught, which is going to be cosine theta. So that's going to be cosine theta. Similarly, this is the component of ex1 along ey naught, which is going to be sine theta or cosine 90 minus theta. Or pi by 2 minus theta, depending on whether you use degrees or and then this thing is just going to be 0. Okay. Okay, so what we have here, we have ex1, just writing that out, we have ex1 equals cosine theta ex naught plus sine theta ey naught plus 0 ez naught. Now what about ey1? Let me redraw this picture. Okay, ey1, maybe I'll not redraw the picture, but let me just rewrite it. ey1 equals something times ex naught plus something times ey naught plus something times ez naught. What is that something? So let's in fact redraw it. This is theta, this is EY1, this is EY naught, this is EX naught. The projection of EY1 onto EY naught, which is this quantity, is basically cosine theta. That's this thing. The projection of EY1 onto this thing is sine theta, but then this is along negative EX naught, so it's actually going to be negative sine theta. Okay, so that's it. So we have expressions for EX1, EY1. We can write a similar expression for EZ1 as well. We have EZ1 equals something times EX naught plus something times EY naught plus something times EZ naught. Okay, because EZ1 equals EZ naught, really this is 0, 0, and 1. There is no projection of EZ1 onto EX naught or EY naught. Well, similarly here it's 0. Okay, so we have three equations here that relate EX1, EY1, EZ1 to EX naught, EY naught, EZ naught in terms of the components of these vectors in essentially these axes. Okay, now we can rewrite these three equations into a single vector equation as the relationship between the axes are linear. So let me write this equation. This is kind of a weird equation, but because the components of these arrays are themselves unit vectors. So it's cos theta, sine theta, 0 minus sine theta, cos theta, 0, 0, 0, 1. EX naught, EY naught, EZ naught. Okay, so this is a relationship, and this is a matrix. So this is basically those three equations rewritten in matrix notation. This 3x3 matrix is an example of what's called a rotation matrix. Okay, what are rotation matrices? Okay, essentially rotation matrices or a special kind of 3 by 3 matrix, at least for 3D. Because we're primarily looking at 3D, the concept can potentially be generalized to many dimensions. A special kind of 3 by 3 matrices that encode the relationship between frames reference frames that are related to each other by rotations. Okay. They have special properties that we shall discuss later. Uh, to describe the rotation matrix that we just wrote down, we're going to introduce notation. We're going to call this rotation matrix R0 to 1. Okay. So this is notation. Essentially, this is a rotation matrix that transforms the unit vectors that make frame 0 to unit vectors frame 1. Okay. So let me just write that notation down. Our notation. This is by no means universal. R0, 1 is rotation matrix that converts the unit vectors of frame 0 to unit vectors of frame 1. Okay. Now, by essentially reversing what we did here, reversing the process here, we can show that if you want to write EX naught, EY naught, EZ naught on the left hand side with some matrix here, and EY naught, EX1, EY1, EZ1 here on the right hand side, then it turns out you can do cosine theta, and then this tends to be happens to be minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. Okay, that is to be shown, but you can show it by essentially going through the process and looking at, okay, what is the projection of x naught onto these three vectors? What is the projection of y naught onto these three vectors? What is the projection of z naught onto these three vectors? So you can derive this. And of course, you would call this matrix R1 to 0 using this notation. Um, okay. And what we have found sort of in this very special case is R0 to 1 equals R1 to 0 transpose. Okay. Notice that this matrix is just the transpose of this matrix. And it turns out this simple relationship generalizes to all rotation matrices. That is, R 0 to 1 equals R1 to 0 inverse equals R1 to 0 transpose. Okay. So that works, it turns out. Okay. Okay, so that's for this very simple elementary rotation. If we had, that's for a very simple elementary rotation that is a pure rotation about the z-axis. So this was a pure rotation E pure rotation about E z naught. If we had a pure rotation about E x naught, say, okay. In other words, we had so we have E y naught, E z naught, and we have E y1, E z1, and where Ex naught is perpendicular to this plane. Then we have, it turns out, Ex1, Ey1, Ez1 in this new case equals, because Ex remains the same, it's a pure rotation about Ex, we have 1, 0, 0 because Ex1 equals Ex naught. And then we have 0 cosine theta minus sine theta, 0 sine theta cosine theta. Okay, so that's a pure rotation about Ex naught. And then we can have a pure rotation about, so that would be called again R 0 to 1, except now these things are for this picture. And if you had a pure rotation about Ey naught, then the picture would look like the following. Then we have Ey naught remaining the same, but something like Ez naught Ex naught, this being the origin, and then a new axis obtained by rotating these guys by theta. Okay, in this case, R 0 to 1, that rotation matrix is going to be cosine theta, 0 sine theta, 0 1 0 minus sine theta, 0 cosine theta. Okay, so what do we mean by that? We just basically mean that if you go ex1, ey1, ez1, that's going to be equal to this matrix times ex naught, ey naught, ez naught. Okay, and that's what we're going to call our 0 to 1 for this picture. Okay, so those are elementary rotation matrices that represent simple rotations. Elementary or simple rotations and corresponding rotation matrices. What about general 3D rotation matrices? Rotations and 3D general rotation matrices and corresponding rotation matrices. And that we shall see in the next video.